the live stream. Okay, whenever you're ready.
For over 8 decades, Los Alamos National Laboratory has been at the forefront of scientific and technological innovation, effectively shaping the future.
Today, that mission continues inside some of the most contained and hazardous environments on Earth. Americium is a synthetic radioactive element, small in quantity but enormous in impact. It plays critical roles in smoke detectors, medical devices, satellites, nuclear cores, aircraft fuel gauges, and more.
When americium is processed, a heat treating procedure known as calcination produces americium oxide, a powder which smears the inside of its container, fighting gravity and resisting removal. Once in this state, the material must be safely transferred for further processing. However, current processing systems are ineffective in removing all the americium oxide from the container.
This delicate material that we process is worth 7 times the weight worth of gold. Just losing grams of this asset could cost us thousands of dollars. That raises the question, how could we safely extract and transfer this material within the hot cell without placing a human at risk?
Our dedicated team of engineers has addressed this issue through testing multiple different designs. Want to know our results? Join us at Aggies Solutions, for when every curie counts.
Picture this. It's your best friend's birthday, so you decide to make them a cake. So you pull the cake out of the oven, you transfer it to the plate, only to find out that there's a lot of burnt remnant left on the pan. Cleaning that off is already a hassle. Now imagine you had to clean it all off because you couldn't just dispose of the pan, because that remnant that was left on the pan was radioactive. It's also worth a lot of money. Now imagine trying to do that with 2 mechanical robotic arms inside of a hot cell. It's a hassle. So, as discussed, Americium-241 is highly radioactive and has many applications. So we are trying to extract as much of it as we can effectively. At the same time, while using glove boxes would be more efficient, it increases exposure to radiation and can be a health risk. The current protocol using the hot cell is tedious and leads to a lot of worker fatigue, which can cause workers to potentially make mistakes and lead to accidents that have big implications.
Current hot cell infrastructure is inadequate for taking out americium oxide residue, and any solution that takes out more residue would be an improvement. But at Untitled Solutions, we like to go above and beyond and make sure that our solution is easy to implement, removes most of the residue, and follows nuclear safety standards. We also like it to make sure that components are sealed off in the hot cell, make sure our solution removes 99% of the residue, doesn't introduce contaminants in order to complete that task, and interfaces with the current hot cell infrastructure manipulators. And we like to use readily available materials to make sure this is easy to implement and cost effective.
We iterated through many different prototypes for our design process and narrowed them all down into 3 specific prototypes. Keeping this in mind, we wanted to abstain to our design requirements while not completely renovating the existing system. To do this, we wanted to replicate the model of what americium oxide truly is like. So to do that, we use an aluminum cup as our crucible, and we implemented sand and glue and crusted to the sides to represent the americium oxide. With that, our first solution will be vibration, where we use a massage gun to repeatedly vibrate the side of the can to loosen up the sand and have it drop into a funnel system. This solution is very innovative, but we knew we could do better. For a second solution, we have an impact an impact solution where we will introduce a piston and some springs that will cock back a mallet and hit and strike the top of the crucible to have it all fall into a funnel. Comparing these three solutions, we found that scraping the sides with a Dremel would efficiently check off all our design requirements, and it will prove to be our best solution.
So, what is our solution? Our solution is the razor's edge. What is the razor's edge? Razor's edge is a high-powered, high-speed rotary tool, better known as a Dremel. So, why did we choose a Dremel? Well, the manipulator gripper arms within the hot cells are more easily able to grab onto a Dremel than other types of tools. Not only that, but as you can see, our Dremel is highly modified. So, in addition to some other features, we have safety knots. These knots ensure that if the Dremel is dropped by the gripper arms, they're able to safely land on the floor and also maintain clearance from the floor to allow the grippers to effectively grab back onto it. In addition to that, we also added a new type of drill tip. This drill tip is made of 304 stainless steel. Why is 304 stainless steel? Well, it is effectively hard enough to scrape all the Americium off the sides of it, but soft enough so that way we're not scraping the inside of the crucible along with it and having that shrapnel fall into the Americium. Now, you can imagine this process can get messy. This is why we included a see-through cone. The see-through cone allows for operators to see into the crucible and effectively scrape the sides. Not only that, but the cone is large enough so that way it covers the entirety of the crucible while still allowing them to go into the center of it. And if you're wondering how the operator is going to turn this thing on and off, there will be a switch leading out of the hot cell where they can effectively turn it on and off.
So another great feature of this design is that it's a rad hardened design. So what does that mean? Well, it's shielded from radiation. And in addition to that, there are no small components such as PCBs or chips that can get irradiated and easily damaged in the process. So we can handle it all we want inside the hot cell. In addition to that, it's at its core, it's a simple Dremel. Anything that you can pick up for about $20 at any hardware store worth its salt. This means that in addition to that, because it's simply a Dremel that's configured for rad hardened work, we can use it for things like stirring, sanding, polishing, anything that you would use a normal shop Dremel for, but now within the context of a hot cell. So when every query counts, we want to ask you, where do you think the razor's edge can take you?
Our design improves upon the current process in many ways. Number one, money-wise. Our process is cheap. It's commercial products, easily replaceable, and also Americium is very valuable. So you want as much as you can, so you can sell it on and use it. It's also, our process is way faster, so it saves time, which also decreases worker fatigue, which leads to less work accidents and more efficient process. And then finally, Los Alamos Labs is the sole producer of Americium in the U.S. So any way we can improve your efficiency helps the U.S. be less dependent on foreign suppliers. That's the conclusion of our slide or presentation. And love to hear your questions.
Questions for Team Actinide Solutions.
So, what efficiency do you think you get with the removal process?
In terms of efficiency, like how are you quantifying efficiency? Like,
Okay, so you had a target for how much you think you remove how would you demonstrate that you can achieve that target?
Well, we can go back to our testing models. These are 3 models that we use to test our designs. This one right here is the one we use for scraping. As you can see the inside, this is the area where we actually work on the Dremel. We just experimented a little bit for the timing, but as you can see, every spot where the Dremel actually hits, it's clear. All of that, all the Americium, or pseudo-Americium in this case, fell back into the crucible and were safely recovered.
how long do you expect the steel tip to last? Right? You want it to wear, right, so it doesn't wear on your crucible. How often does it need replaced? What's the that replacement process? Is that can that be done in the hot cell, or does that need to be you got to go in and swap out?
Yeah, that can all happen in the hot cell. We even thought about having like a tray because it's disposable. You have to throw away the tip after because it's contaminated. So like have a disposable bin, and you could have like extra bits in there that you could have a mechanism where you just push it in and then replace the tip.
You think is it a place every time thing?
No, I don't think so. We didn't do the calculations, but it shouldn't be too expensive and not too much of a hassle.
Something also about the Dremel too is that it's very interchangeable. So yes, like these parts will wear, but it will function essentially like a regular Dremel. Chances are, if you're using that Dremel often, you're not replacing it like every week or so. It's probably going to be like a year or a month or so. So they'll have a long longevity within working in a hot cell.
I had a question about your design trade-off matrix, your decision matrix. You had three concepts that you were comparing, and you had various criteria. One question was just a clarification. What is renewability?
So basically, it refers to whether or not the crucible remains intact during the process. As you can probably tell from the other two crucibles that we use, both of those were damaged in the process. The one furthest to my right here was the one used for the massage gun. This side was dented because of the massage gun pounding against it to cause vibrations. This one, we weren't able to make the pinball simulation, but we were able to simulate the same process by essentially turning it upside down and smacking it with a hammer. Just from one light smack, crushed the entire thing. So both of these failed in that aspect, as in they didn't maintain the crucible and make sure that we did have to replace that.
Okay, so renewability is the ability to reuse what's in the hot cell.
Yes.
And then the other related question is, as you went through those solutions, so you got some prototypes, was there any role of the subject matter expert in helping guide whether prototypes were realistic or addressed the criteria that were wanted?
Yeah, we later reviewed our testing with one of the mentors, and they confirmed that this caked-on sand with the Elmer's glue was very close to indeed what we would see in it with Americium oxide.
Thank you.
Maybe more just a observation from TJ's question that Dremel head replacement is very small in the manipulators, and may not be aware of the depth of the hot cell window. Also makes it hard to see really fine things too. So it's something to sure.
Okay, thanks, team. Hey, Marcus, come on up and get settled in. Are you nervous?
No.
You nervous? Okay, so team, bottom is down. I mean, bottom is down.
It's actually pretty
Got it? Good. So what's that just on cell phone? Whenever you're ready. Students, so that.
Automated rotating collection utility system, ARCUS. Imagine you are dealing with a highly radioactive material and you have a contained space and you're trying to get it out of the container without touching it. That's a challenge that we solved. With Arcus, we're transferring from mechanical to automated.
Values with LANL, they care about family, they care about you as a human being.
Safety, I would say, is number one priority of the laboratory.
Making sure that you go home every day the same way you came in.
So Americium is very dangerous for the sake of it emits a very high emission rate of particularly gamma radiation and neutrons.
It can build up and there's a lot of radioactive that goes with that.
The amount of americium that's going to have to be produced over time is going to increase. Eventually you're going to get to a point where the entire operating team will get dosed out.
Yeah, it is very dangerous.
How many people would we be helping if we were to solve this issue effectively?
Truthfully, the world.
Americium is incredibly valuable, so why are we putting our engineers in so much danger just to let so much of it go to waste? Our team knew for a fact, there has to be a better way. Meet Arcus, the automated rotating collection utility system designed by 6 brilliant engineers. Arcus is here to tackle the stubborn americium residue that clings to crucibles. Using the hot cell's mechanical arms, just place Arcus on top, pop the blades open, and press a button. That's it. Arcus spins a full 360 degrees, scraping away residue with full automation. No manual handling, no extra exposure. The result? Safer operations, cleaner crucibles, and up to a 10 times increase in production. Less risk, less waste, more americium. It's simple, it's efficient, it's Arcus. Arcus, controlled rotation, complete recovery.
Now, how are we currently solving this issue at LANL? We use a glove box, so the operator is exposed to high radioactive emissions. That puts their safety at a high level of risk. Not only that, but when an operator goes to extract it, they're currently using a metal scraper to scrape the edges of it, right? And that's not efficient. They're removing around 85 to 90% of the crusted on americium. Also, the operator takes 15 to 20 minutes to do each of these processes. That results in operator fatigue and also human error. Now, how did we come to our solution? We wanted to combine the operator's health and what they needed combined with a managerial yield aspect. So we designed all of our solutions upon that. We ended up with a working prototype, which we simulated here.
So our first design was a inertial driven spinner. Works much like a silent spinner, but it rotates. Our second design was like a hand drill and it scrapes the sides. Finally, we landed on Arcus, our automated rotating collection utility system. It places our operator and our control board outside of radiation and keeps our radiation hardened device inside effectively. So our design requirements, we decided 5 things that were important to us. Firstly, we wanted to extract 95% of our oxalate powder, which is valuable. We also wanted to reduce 90% of radiation on our operator system. It takes into mind their safety as well as their productivity on LANL. Thirdly, we want to optimize the current equipment. This includes the crucible, which we have a copy of, and the pinchers. This minimizes any capital loss. We want to do this in a timely fashion and prioritize our operators' ergonomic. So the current method does none of these things, unfortunately. For our iterations, we were able to achieve some of these, but it was only through Arcus that we achieved all 5 of these and we went beyond.
Now, there's a reason we're doing what we're doing here with Arcus, right? For one thing, reducing opportunity costs. Americium sits at a gram rate of $1,000 per gram. That means with the 15% increase in extraction that we can do with our device, we'll gather about $4,000 extra worth of americium in terms of extracting it. But it's not about the monetary value, is it? It's also about employee safety. As of right now, under current circumstances, employees are exposed to around 50 millirads per hour of radiation. That sounds like a lot. It's not very sustainable for employment. That is why with our device, we would reduce this rate to 0.01 millirads per hour. Now, we understand that the pincers at the end of the mechanical arms aren't exactly very easy to operate. That is why with our design, we focus on making sure it's easy to lift up, easy to use, and requires almost no physical strain from the operators, given that it's automated. And if we're talking materials, the LANL crucible has a hardness of 88. The material we'll be using for our fan blades is going to be a little softer than that as to not damage the interior lining of the crucible, allowing us to seamlessly navigate around the obstacle of the interior lip of the crucible.
Now moving on to our final design. So first we have our initial design drawing, which we saw before, as well as our CAD model. And now for our prototype. As you can see, the gear is rotating and the fins rotate along with it. The way that this would be applied within the hot cell would be that the operator could use the pincers within the hot cell to take RCS and guide it over the top of the crucible and feed it in. After that, we'd be able to push down on this, which would be a ratcheting mechanism to allow the wings to open. Let's take a closer look at that. As you can see, a downward press actually allows these wings to open. How? These wings are actually four-bar linkages, which allows the expansion and the compression. And these are designed in a way so that way no joint is cantilevered, meaning that no joint is attached only at one side, which allows smoother expansion as well as stronger joints to lessen material costs. Ideally, this would be used on a workbench within a hot cell with a reel of wires, so that way the operator can pick up Arcus, guide it wherever it needs to go, and place it back without fear of tangling the wires when other operations are needed within the hot cell.
Moving on to the electrical design, I want to talk about how Arcus operates. With Arcus, as you've seen in the previous slides, it aims to, for the most part, to automate the extraction process of Americium. So in order to do that, it has a functionality of having a servo or stepper motor within the hot cell itself. That will be adding carbon, make sure that it doesn't degrade or anything like that, and as well as a system outside of it, including LCD, power system, and microcontroller on the outside of the hot cell, so that operators can interact with it individually. As for the system, this is what the system looks like, essentially. At the outside of the hot cell, operators will be able to interact with the system itself, and because of the simplicity of the system, it's very versatile, being able to be applied to many different types of hot cells, no matter the size, restrictions, and dimensions. And additionally, it's a very simple design, for ease of use, allowing for operators to only interact with 2 buttons, which is, again, very easy to operate.
Human life always comes first. That's why within the hot cell, if it acts as a shield for radiation for the operators, reducing up to 99% of radiation that they are exposed to. What this means is that operators can operate for longer and that more cycles can be done of processing of the Americium. Arcus extracts as much of the Americium as it can from the walls of the crucible. Doing this reduces the amount of waste, which is highly contaminant to both humans, animals, and the entire ecosystem. Lastly, the automation of this whole system means that the process cycle is quick and it's efficient. Aiming under 2 minutes, that frees up man hours of the operators to be allocated elsewhere and to use their technical expertise where needed. Arcus is not just a tool. It is the foundation and the pathway for a future and safer and autonomous processing of materials, or control rotation and control recovery. Thank you.
Judges, any questions for Team Arcus?
In your video, you made a claim like 10 times production increase or something.
So after talking with some LANL employees, we said that the glove box is quite small, so we can only place one furnace. If we're to move to a hot cell and utilize our system, we can place up to 10 more furnaces. That's quite a conservative measure. We're told we can place up to 50. Thus, by increasing the number of crucibles we can do per cycle, we can increase production at the same time to 10 times more.
So it wasn't just a claim, you actually have that's what I wanted to know. Thank you.
Where did you come up with the 2 minutes per crucible for cleaning time?
It was primarily because of the way that the system operates. As you can see here, it operates with a stepper motor, which in itself is pretty strong. It has a high torque, able to scrape against the walls. And so with our calculations, we were able to determine that only with a couple of rotations of the stepper motor, or revolutions of the stepper motor itself, we'll be able to scrape not only against the sides, but also the bottom of the system. And so that's just what we determined based on that.
So based on how many rotations you assume it would take to
And how did you decide how fast you spin and how much force you apply?
So the way that we determined that was primarily just based off the motor restrictions themselves. The stepper motor that we would like to use is a rad hardenedness stepper motor that has a certain amount of torque that needs to be applied. And so utilizing the maximum torque that it has, we base the system off of that and just kind of utilize that same number whenever determining how fast it should go, because the mechanism itself has its own weight. It has to be dragged across a gear train, as you can see right there. And so it's very important that we don't overstep and apply more torque than what the motor can easily do.
Anything else, judges? All right. Thank you, Team Marcus. All right, so Team Revolver, come on up. Settle in. So down arrow to advance. Down. Who starts? Down the advance. Spread out. So but wait and start on my cue. Okay. Team Revolver, whenever you're ready.
Howdy, everybody. We're Team Revolver.
A joint radiation research initiative by Revolver and Los Alamos National Lab. Critical chemical transfers have required scientists to work manually inside drug processes. It is precise work, but it is dangerous. Dedicate our lives to science. The manual handling asks for too much in return. Despite your best protection, that invisible dose accumulates year after year, quietly unraveling the very biology you strive to understand. This is the Revolver manifold system. Watch as it automates the complex routing process. To prevent contamination, the system immediately initiates a water flush cycle, clearing the lines and draining the waste automatically. The manifold then rotates to route the specialty DHCP chemical. Once the transfer is complete, a final high-pressure air purge clears the system entirely, resetting the manifold for the next cycle without a single human hand entering the hazard zone. The engineering behind this is robust. An actuatory rotary design couples with a remote connector, ensuring a perfect seal that separates the mechanics from the chemistry. This technology allows us to move from dangerous manual transfers to full remote operation. The operators remain safe behind the glass, controlling the process with precision, eliminated exposure risks, and a healthier workforce. Revolver manifolds, switch Revolver, stay safer.
So what is the challenge that we are trying to solve here? Challenge is that scientists have to manually change the pipe for chemical transfer, which is unsafe, inefficient, and not automatic. So what our solution is trying to do here is to try to make it more safe, more efficient, and more automatic. As you can see, these are past historic incidents because of glove box mismanagement. So first hazard we have is glove box explosion in 1976. And then we also have glove box breach 2000. And takeaway from here is that we need to avoid this, and our product aims to end this.
when we were researching about this project and our needs, we found out 5 main key design criteria. The first one being that the containers need to be mutually exclusive and there should be no cross-contamination when the liquid flows. The next one being there should be high throughput so that the liquid can flow from one pipe to the other pipe in and out easily in split seconds. And we need to be dealing with 4 containers here. Each of these 4 containers have 4 valves. So we need to take into consideration about this too. And we also had to make sure these processes are simultaneous so that all the chemicals that needs to be processed in the next batch are processed in the singular batch and is moved on to the next phase for processing. And the most important one, all of this happens within hot cell. So we need to make sure that our manifold system is radioactive resistant. So let's take a look at our 3-step iterative process. First, we made a simple manifold, which is just a pipe that connects between different cylinders and has a valve in it. The problem with this one was it was not scalable at all. If we increase the number of cylinders, we would just have a big web and it would be very difficult to manage in the long run. So we moved on to make a rotatory system with 2 pipes. The problem with this one was it was just very difficult to maintain, to manage the cross-contamination between the 2 pipes. So what we decided was we just have one pipe that uses pressure differential between the 2 ends and moves the liquids in the same pipe in and out. This way, we can manage the contamination because the flushing and the sprinkling system within it would be easier to maintain.
With our final design, we were able to resolve 5 massive improvements over the original process. First, we were able to eliminate cross-contamination using a robust flushing system. With this, cross-contamination is a worry of the past. Now, also due to the autonomous nature of our product, operators will never have to put a hand in to ensure chemical flows. Instead, they'll interface with a software from a remote location, essentially and virtually removing any risk of dose. And since this is a software-based application, we are able to optimize the transfer time and maximize chemical throughput, ultimately maximizing process efficiency. And the most important part is that this is a fully scalable solution. No matter how many chemical tanks that you need to implement, our product is able to adjust to that with minor improvements only. Now, let's look at the design blueprint. On the left, we have our chemical tanks as well as our additives, hydrochloric acid, DHCP, and oxygen. On the right side, we have a solution reservoir, a water reservoir, and a vacuum pump. And in the middle is our revolutionary technology, the revolver. The revolver acts as an interface for our left side to be transferred into the reservoir, and then the revolver again will transfer from the reservoir to simultaneously pump fluid into any amount of tanks in any configuration. Now let's take a closer look at this revolver technology. As you can see here, we use state-of-the-art precision machining technology to ensure that this is both a robust and enduring system. Now, let's take a look at a little demonstration of our prototype. First, our prototype has the ability to rapidly and accurately index through the use of a linear rotary actuator, which means it spins on its axis to choose which pipe it wants to use. Then, when it wants to couple, it's very secure. Through the use of C-rings, leaks will be minimized via pressure. And then when it's time to actually move the fluid through the pipe, we will induce pressure differential, which will push the liquid into the containers at a rapid speed. And finally, when we wish to decouple, we will simply retract the piston and we are ready to re-index.
Now let's look at an implementation of our system. So this is a rotary system that has a left and a right manifold. Each manifold has 8 pipe fittings. On our left side, we would take in all of our chemical mixtures and pure substances and fit it into the pipes. And on our right side, we would run the chemical. We would have pipes that lead into each of the chemical mixtures and a waste disposal system. Now let's take a look into an individual fluid process. So fluid can go in and out through our system. But what if we want to take in fluid 1 and take it into tank 2 instead of tank 1? Our system would first decouple, and then our system would index to align the fitting from fluid 1 to the fitting to tank 2. And finally, our system would recouple and ensure correct sealing. This is done through metal C-rings and gas material, so which will be compressed by our piston. And finally, fluid can flow in from our fluid 1 can flow into tank 2 instead, or tank 3 or tank 4. This is based on how many holes we have in our rotatory system. Here's our system within its housing and the linear rotary actuator on the side.
Alright, so what makes our product special is that, first of all, it comes down to 4 key facts. We have electrical indexing, which allows us to be able to place our electrical equipment outside the hot cell, which ensures that we can avoid any radiation exposure and damage to it. Next, after, we have our air-driven pumping, which ensures that we can rapidly release and intake chemicals to their designated location. And furthermore, we have our contamination-proof routing, which uses a robust system of pipes to ensure that we can avoid cross-contamination as well as reliability of the system. And finally, we have routine maintenance, which allows for the simple replacement and adjustment of the manifold to inspect it and ensure that we can replace C-rings as to where it determines. And we have our performance indicators as shown up on the slides. So to summarize, our problem was that we had a manual overhead operation, and our solution was that we had a enduring autonomous rotary system, which has been shown to have lasting and immeasurable benefits to the end user as a whole. Thank you.
Judge's question for Team Revolver.
I remember at the beginning you talked about it being bi-directional. Understand how that played into your.
So earlier we had 2 pipes running through the center of the same manifold, and one of the pipes would take the liquid in to one of those tanks, and the other pipes would bring it out and bring it to the other tank. Instead, we are just using one pipe that would just take the liquid in and out, using the pressure differential that we create on both ends, making the pressure difference.
What in your design guarantees that you don't have any residue left over after transfer?
We will be running one of our intakes on our left manifold is water, so we will be running water through the system. If you want to swap chemicals that go into one tank, we can run water through, and we would take pH readings of the water in our waste disposal system to ensure that it's neutral. That would ensure that there's no acidic remains, and we can have no cross contamination.
You know the amount that you have to do for your flushing, as far as again volume, like how often you're going to have to empty your waste.
All of our tubing is 3/8-inch tubing, and we would. It really depends on the distance between the tank and the manifold, but I don't see it being a lot, and we would just have to run maybe 2 or 3 flushes just to get the pH level of to make sure there's no acidic remains inside our piping. But it shouldn't be too much, and it depends on the container. I don't see us having to replace it for a couple of weeks.
Any else, judges? All right. Thank you, Team Revolver. Okay, so Team Project Illumina, come on up. You settle in. Something for all of you as you're watching your event mates or competitors or evil empire, whatever you want to refer to them as. When we're finished with the next 4 presentations, the judges will convene in the room next door and we'll finalize the results of the judging, and then you will stay in here and you will do a bit of a survey, like a little after action survey, but then you'll also get to vote the People's Choice Awards. And People's Choice Awards include Best Prototype, Best Video, Best Overall Presentation, and then Most Feasible. Okay, so be thinking about all of those categories because you get to vote. And you must vote on somebody other than your own. Otherwise, it always ends up a tie. I don't know why that is. Okay. Holy smokes. off my battery here. I'm a little concerned. Okay, who's starting? Anybody know who's starting? Yeah. Down. Down arrow is forward. Okay. Down arrow is forward.
Can we get the guy that's running the computer to play the video?
Yeah, I talked.
But he will.
He said that I
It's
would
his
just
job.
have to say that.
It's auto remember. Okay. Whenever you're ready.
Welcome to Project Illumina, where safety is our first ingredient.
In baking, you can try again. In nuclear processing, you can't.
36 helpers die within a short span of time due to radiation
Americium
sickness.
241, both known cancer causers.
This program on Thursday, at least 7 people are dead.
Another 134
suffered
from
exposure to nuclear waste.
Americium 241 saves lives, but moving it puts them at risk. We've engineered the perfect recipe, one where safety is a top ingredient. Welcome to Project Illumina, where we protect people by perfecting the process. In the current americium processing industry, the calcination process is used to create americium oxide powder that can be stored and shipped as a product. However, this process can be very time-consuming and also results in a large amount of radioactive waste that becomes troublesome to treat and dispose of. That's why Project Illumina proposes a new solution. It takes an entirely new approach that targets these main problems. By burning the resin beads containing the americium, instead of using an elution to separate the americium from the resin beads, we can save time and the environment while creating a safer strategy. Together, at Project Illumina, we can make the difference and prioritize safety.
Every day, Americium 241 saves lives. It's used in medical devices, in smoke detectors, and even in industrial distribution systems. However, the process of americium calcination is extremely dangerous. It's unsafe, takes a lot of time, and creates copious amounts of radioactive waste within our environment. This is the problem that we are here to solve, but we are the solution.
So when it comes to transferring the resin beads from the resin container into the furnace, we have to remember that the design process has to be simple, cost-effective, and most importantly, that it speeds up and improves the calcination process. So here are our design requirements. Number 1, reliability. Our design solution has to work multiple times without fail and ensure that it doesn't harm anyone else or cause any leaks or wastage. Number 2, safety. So we need to ensure that our workers are not put in dangerous situations and that our workers are always being prioritized and that we keep them safe and the environment also safe. Number 3, longevity. We have to ensure that the product has a long life cycle. Number 4, affordability. By keeping the product affordable, we can make the product more feasible and we can ensure that the product is put into timeline. Number 5, heat resistant. We need to ensure the product is heat resistant because it's going to be coming into close contact with high temperature furnaces, meaning that heat resistance is a must and an absolute need.
By keeping the design requirements in our mind, we evaluated multiple potential solutions. Our first option was a hood system. Now, a hood system is a simple way to transfer the beads from the resin column to the furnace. But while transferring, it might swing and might slip, so which directly impacts our safety as our design requirement. So now we move on to our second solution, which is the use of the mechanical arms, which is already present in the onset. Now, these mechanical arms have the ability to control precisely and also has a remote control the ability, but it lacks the ability to grab a size of a container, which is the crucible. And so this also impacts the precision and the safety. Now moving on to our third option, which is a solution. Now this is a hybrid approach. The use of tongs to grab the crucible, and using the mechanical arms, we can control it remotely. Moving on to our next slide, As you can see from the decision matrix, by clearly stating the design requirements and objectively evaluating our solution is both safe and can be implemented immediately.
Okay, so now we're going to show you our prototype. So when you're sorting the Americium out of the spent nuclear waste, it flows through a resin bead column, and the Americium will collect on the outside of the resin beads right here. And then in order to extract the resin beads from there, we're going to use this ball valve that we designed. And we're going to open the valve and drop the beads into our crucible. And then once we have the resin beads in our crucible, what's next is we need to put the crucible into the furnace, right? It's a pretty simple process, but keep in mind that we're trying to reduce the radioactive exposure for our workers. So we're doing all of this in a hot cell, right? So these two jumper cables are acting like pinchers on the end of the arms in a mechanical arm in the heat cell. So it limits our dexterity, but with this tool, we're able to more easily grab the tool, pick up the crucible, and have a stable connection with the crucible so that we aren't dropping it and we're not having to mess around with a weak connection. And the reason we went with a design so simple is because if you use any electronics or you try to automate this and you have electrical systems and computers built into your design, the radioactivity will worsen the connections and it'll decay the electrical components over time. And so in order to increase the longevity of our product, we strayed away from electrical systems as much as possible inside of the hot cell.
So what are some of the key components of our design? Well, we have a crucible made of alumina because this material doesn't react poorly to nuclear waste, and it also can withstand heat. We also use mechanical arms because if it ain't broke, don't fix it. They all are familiar with this kind of equipment in the laboratories. We designed our own set of tongs in a way that grips it around the various sides of the crucible, which helps to improve stability whenever transferring. And on top of this, we also had a ball valve that we specifically chose to just improve the flow of the resin beads.
This all sounds way too good to be true, doesn't it? Well, let's take a look at the numbers. So first, we have our ball valve. We estimate that to be only $40 per unit. Then we have the specialized tong that we designed to carry the crucible into the furnace. We estimate that to be at $200. And finally, the crucible itself that is melting the resin. We estimate that to be around $350. In total, our product sits at only $590. I would say for a product that can last from 5 to 10 years and greatly improve the efficiency of the process, I would say $590 is a pretty sweet deal. Now let's talk about the impact of our product. So, as stated earlier, we can greatly improve the efficiency of the calcination process. We estimate that our new design, can improve the process from around 24 hours to only 8 hours, increasing the efficiency by over 200%. Next, we believe that our new product, can greatly reduce the amount of waste generated by the current calcination process, generating the Americium. And finally, of course, last but not least, we also can greatly reduce the amount of worker exposure during this Americium production process.
We urge you to think about the safety of your workers. Think about how efficient this process could become and how simple it could be. We urge you to use our solution. We are Project Illumina. Thank you so much.
Good job, Project Illumina. Judges, any questions for Project Illumina?
I noticed you lost a few resin beads as you were transferring your ball valve into the crucible. So how would you prevent that in the hot cell?
We will control the motion of the ball valve properly. Right now, it's we are using.
So I would say that we're gonna control the ball valve, but the most important part is that the resin beads are a little bit squishier. These are hard plastic hitting hard plastic. And so the resin beads are going to kind of lose their momentum and not bounce quite as easily as it did against the surface.
The actual process, the ion exchange process, is done wet, but your demo you did the transfer dry. So you imagine that you will dry the beads before you transfer them, or do you need to think about ways to do wet transfer?
So in terms of beads, yeah, we would in our actual process keep the beads dry. We would have to dry them beforehand. We might not have mentioned that, but we do assume that, yes. We would dry the beads first, then we'll do this entire process dry. But that's a major component, so yeah, thank you for bringing that.
The solvent will be extracted from the resin column, and there will only be the beads left, which is coated with the Americium. So it will be dried out.
You use the jumper cables as your
Mechanical arms.
But that was, I guess that was my question. Is, do you need to put something on the mechanical arms to do that, or is that already?
It's just
that,
with the
you were
yeah,
just meaning
it's just,
that.
yeah. We are just mimicking the mechanical arm. Yeah.
Anything else, judges? All right, thank you, team. Team Superheated, come on up. Team Superheated.
I'll get you.
It was the guy in blues. Yeah, back there.
Yeah.
Yeah, no, I was going to use other bits. But yeah, he said
I was slowly opening.
Okay, student, let's settle back there, settle. Whenever you're ready.
Howdy.
Howdy.
This is Superheated, and here are the problem and plausible solutions for furnace designs for burning resin. If we may, we would like to start with a short video.
I don't want to set the world on fire.
The story began with the development of the first nuclear bomb in the 1940s.
Here is far greater than financial, since it involves highly toxic nuclear
waste from weapons production. A 1992 law specifically banned it.
But it doesn't have to be that way.
How curious that something so dangerous can be so helpful. Americium, a byproduct of plutonium production, can be found in crucial safety appliances that protect humanity.
This first alert smoke detector can give you early warning, more time to escape.
Los Alamos produces plutonium for the common defense, and its byproduct of americium is useful but requires careful purification. The current chemical processing of americium is too slow for the magnitude coming from the plutonium. What if we were able to skip that chemical process, increase the production per run, and reduce the time it would take? We have that solution at Superheated, extreme heat into cleaner outcomes. Are you ready to change the future?
I don't want to set the world on fire.
First, let's talk about the problem. Let me give you a little bit of context. So in the 80s, when the Rocky Flats production facility shut down, the domestic production of americium was almost zero. We were relying solely on the Russians and foreign imports of americium. However, in 2020, Los Alamos National Labs was beginning to ramp up domestic production of americium again. However, the current chemical process is quite problematic. With purity, if it's not pure enough at the end result of the oxalate that is formed, it has to be disposed of and becomes even more radioactive waste. Time, the current process currently is too long, and we are trying to find ways that we can reduce that time. And feasibility. Right now, the process is quite dangerous to the workers working in the glove boxes,
And to make our process better for americium production, we need to achieve 95% purity in each batch.
that means less than 5% of any contaminants, particularly ash, from the resins. To maximize the surface area to volume ratio, that in a 800-degree centigrade oven, we want to produce more than what's the current check benchmark for Los Alamos. They're doing 1 liter per batch. We want to do much more than that. Additionally, to have safety concerns in mind, whatever our solution is has to be able to contain any and all combustions.
So now for our first solution, we thought big. Instead of calcination using a furnace for several hours, we could use lasers to heat up the resin. Lasers are highly focused energy, which can instantly vaporize the resin. And we can use optics to change the intensity of the laser. Now, lasers have a ton of industry applications that are very great, meaning that it's commercially viable, especially in the semiconductor industry. The problem with lasers is that they're very complicated, so they're very expensive. They're going to take a lot of maintenance, and most importantly, they're going to use up a lot of research and development. So that's why we didn't end up going with it, because overall, it's just not quite what we're looking for in terms of getting a product out quick.
For our second solution, to achieve uniform heating, we use indirect contact heating process. The main goal of our heating process is high temperature. That is, like, it should go up to 800 degrees Celsius. So here we use like high temperature heating elements such as candle or silicon carbide air heaters. We can't directly keep our crucibles on top of the heating elements, so we are adding another layer like called thermally conductive heat layers. Since we have multiple layers, we can get like more yield out of it. Currently, we only get like 1 liter of. Currently, you can only heat up to 1 liter of resin per batch. But if we do this, we can use multiple batches and then get more out of it. When we vaporize resins in this kind of a chamber, we expect more vapor to come out. So in order to escape the vapor, we also have constructed a vent pathway in order to just let the vapor out and get very pure Americium powder at the end.
So we really liked the stacked idea, so we wanted to lean a lot more into it. So we have a small demo there of what a possible inside of a furnace could look like. With the multiple layers, we're able to maximize the use of any given volume. Right there is shown 3 layers, but we could have upwards to 5, maybe even more layers, depending on the size. And inside the layers, we can have a new type of crucible that we have designed. These new crucibles are a lot flatter, increasing the surface area, making more even heat, reducing the ash, ensuring that we reach the purity that we need. As well, they have an oval shape. This prevents edges that could possibly cause the product to get stuck on, and this makes the extraction process even easier. As well, you can choose how many you have in there at a time. So make sure you don't accidentally make too much. You can reduce the amount you have in there in this given go. And with each one containing at least 1 liter of a product, you can do several liters in one go for significantly less time.
Then for our final design and the design we ended up going with, this is where our engineering brain kind of combined with our business thought process. So we really liked our idea with the stacked layers. We really think it improved productivity. But we thought it would be a lot easier for Los Alamos to implement an already existing industrial furnace, right? Instead of creating a custom theoretical furnace. So we scoured the internet looking for the best possible industrial furnace to fit with our system, and we found the ST1500. Now, what we really liked about this furnace is 3 main reasons. First one is dimensions for the internal chamber. It has 24 by 24 by 24 inches compared to the current Los Alamos furnace, which only has 5 by 4 by 4 inch internal chamber. So that's a great upgrade in volume and therefore a great upgrade in possible production. Next, the heating. It can heat up to 1500 degrees Celsius, which is way above the minimum threshold of 800 degrees. And lastly, the main component, it has a ventilation system in the back, which circulates air throughout the chamber, making sure that everything is evenly heated through convection heating. That way, everything effectively vaporizes in the chamber.
And now we have come full circle from our problem to our solution. We will achieve the results we want of increasing domestic production of Americium through making sure that our maximum surface area crucible design gets the 95% purity or greater, through decreasing the time from the old chemical process and drying process taking almost 5 to 6 hours and decreasing that to 2 to 3 hours in our new furnace, which is reducing the time by half, and feasibility. These can be implemented into the hot cells instead of the glove boxes, making it more safe and efficient for the workers and operators.
So now that we talked a bit about how we could increase the production of Americium, let's talk about why it's important.
So currently in the short film that's already being implemented, it's used in smoke detectors and medical devices. And for the long term, there's currently research going on and using it as a power source for space exploration. And organizations such as NASA is already doing it. But most importantly, for specifically Los Alamos, this is a way for them to increase their profit because currently they're selling it to the DOE. And also, not only are they turning something that was just radioactive waste, they're now turning it into something that could be sold for approximately $1,000 per gram. And reducing the need to have like underground radioactive waste storage that could cost up to $100,000 per waste bin. And thank you for listening.
Judges, question for Team Superheated.
So, how are you manipulating these crucibles?
You're talking about with the manipulator arms in the hot cell?
Yeah, sorry, is it just the arm that has to grab those and move them around?
Yeah, so this would just be the inside chamber of the furnace. We didn't model the entire furnace, but we did design them with these handles on them to be easily grabbed through the arms, as well as the furnace itself has three controls. It has an on and off, and then a temperature dial, which also needs a arms.
You know, so that's scaled, right? So I saw on there it's supposed to be 17 inches. So that's
yes,
quite large, right? To hold a liter of water, or liter of stuff, this is less than a liter. So it's trying to think about mass here, trying to hold this thing at one point. Do you know how strong these manipulators are and how adept they are at moving these around?
So the material,
pretty shallow walls. I'm worried about stuff sloshing out, or you're losing material like as you're moving around.
yes. So when we were thinking about this, we did consider the loss of material. So the resin beads will actually be solid when entering here and vaporizing. On top of that, this is scaled down, so we did add this outer lip to prevent as much spillage as possible. And the material strength, we were talking about, being able to lift it. We will be using the same material as the old crucibles, which is, I believe, it's the Haynes high heat-resistant metal alloy, which we did try to run through some calculations to see if it would be strong enough at the temperature requirements, 800 degrees Celsius or higher, to make sure the handles wouldn't snap off.
How would you transfer your final product out? Once you have it ashed on the tray, what do you do next?
I believe that it would be a similar process as putting it in. We take it out, and although the crucible is different from what the other groups used as their example, we believe that even their products could be used on it to ensure that all of the product is removed from it.
So how do you empty a tray?
Simply, so there's the robotic system has it so that it can tilt. So they can simply take it and dump it into a bin. It's literally like putting down a pizza pie. Not say a pizza pie. It's like think of a patty. Yeah, think of a patty.
I
don't remember hearing, maybe you said it, do you consider the potential radiation damage to electronics and the furnace itself when you selected? It looks like you went for a commercial product.
Right. When we were selecting the furnace, we made sure that no electronics were directly exposed to the materials inside during any moment in the process. So everything is insulated. No degradation will occur to the actual material.
And you chose, even though your process is 800C, you chose a 1500C furnace. Is there any rationale for doing that?
So our rationale for doing that is what is going to lead to the increase or the decrease in the amount of time. The specs on the furnaces we looked is the heating rate is measured in temperature Celsius per minute. And if it has a higher capacity, we found that those usually have a higher ramp up, so it can reach that 800 degrees Celsius target quicker than in the old furnace.
Okay, thank you, team. Now it's time for Team Arts. Come on, Team Arts. Good job, team. Good job. Be thinking about your favorite prototype, your favorite video, favorite overall. Success. Second table. Okay, so with clicker, yeah. Okay, whenever you're ready, Team Arts.
Since the dawn of the atomic age, the challenge has remained the same. Distance is the only absolute shield. But distance creates a vacuum in precision. To move Americium resin, we chose geometry over machinery. To bridge the 6-foot gap, we didn't look for a robot, we looked for a tank. A 6-foot, 316 grade stainless steel rotary table. Automated by industrial torque, but finalized by the human hand, reducing the most dangerous path in the cell to a single automated rotation. We are ARCS Americium Resin Carousel System, engineering the radius, leading the way.
How do we get the resin from the columns into the furnace in the most efficient manner possible? This is where our product comes into play. ARCS, the Americium Resin Carousel System. Nuclear engineering has never been limited by physics. It's always a matter of what we deem is safe. Americium DGA resin processing is inefficient. It's slow, it's manual, and it's unsafe. Right now, it's very, very labor intensive. We have workers that are handling Americium with their hands through glove boxes. Glove boxes have proven to keep nuclear radiation outside, but only for a period of time. This reduces efficiency by a major amount. And what happens after the Americium? Well, the radioactive liquid waste, which acids are currently being used to process the Americium and resin, it's being thrown out in large volumes without any concern at all. And this process has been going on since the 1960s. We need to bring some change.
With this problem, we came up with the following design constraints that fall into the following categories. These are regulations, long-term reliability, legacy systems, throughput, and ease of use. The Our design had to fit the facility's regulations, so no Bluetooth, cameras, or microphones. We had to ensure that our design fit within the given hot cells. Our design had to be feasible in the long term, so we stuck to mechanical systems and, when necessary, only radiation-hardened electronics to avoid radiation degradation. The design had to fit the given. Any modifications we made to the resin cylinders had to maintain its general dimensions that were given, which were 5 inches in diameter and 3 feet in height. And we had to maintain a 1 liter per run per day minimum throughput. The desired throughput is provided by subspecialists. And lastly, and importantly, we wanted to ensure that any interface between the mechanical manipulators and our design were stuck to simple single-axis movements to ensure efficiency and ease of use on the operator's behalf.
So onto our solutions. So the first design idea that we had was the auger elevator. So the mechanism that would occur is that the resin would fall into the hopper, you see on the left, and then it would be driven by a helix screw, and it would go into a funnel at the top and then drop into the furnace. The problem with this is that it uses an electrical motor, which is radiation prone. There is a chance that the resin gets stuck in the screw, which is very bad for the residue. And we don't have a way of measuring the amount that we're putting into the system.
So then we decided that we wanted to go to a completely mechanical system with zero electronics. That was the manual resin carousel. And in that system, we had a funnel that would be carried by the operator and a carousel that was actually moved by the operator's hand as well. But we realized this was actually more inefficient than the legacy system. So we moved to our current solution, which is a hybrid of those two.
So for the first step, how are we going to dispose of the resin? So what we're going to do is we're going to use a butterfly valve. The butterfly valve is going to be actuated pneumatically. This is through a mechanism actually with bracket pinions. And the solenoid is going to be it's going to be external outside of the hot cell. So there's no electrical components being radiated. And then there's going to be tubing that goes to the mechanism. And then from there, when it's open, we use a 3-2 solenoid that knows open and close and has reset points. And it goes into the hopper, which will then land on the crucible as a container on the carousel you can see there.
And with this carousel, we believe this is the most efficient solution that is possible. So first, we're taking the linear slide mechanism, which is actually mounted onto the carousel. So the operator, in a single axis degree of movement, pushes the slides and engages the crucible, which is in this case a cardboard box. And once it's pushed up, we have the 4-bar linkage, which is used to increase the height on the z-axis of the system, and that is so that we can actually engage with the crucible and set it up and down. Then it's rotated to the furnace, and the operator is again able to use a stepper motor control with a joystick, and that jogs the carousel in a circle. All of our solution components, all of our electronics for the stepper motor, those are outside of the hot cell, and the stepper motor itself is a rad-hardened stepper motor. The carousel underneath it has a load cell where we're able to quantify how much resin we have collected by taking the difference in the mass of the system without the crucible and then with the crucible. And then we have a furnace which with a rack and pinion system, and through the use of a vertical pull, the furnace door is able to open. So in this system, we optimize specifically for ease of use by the operator. With these mechanical arms, they're very complex to move. A single axis motion is a lot easier for the operator to achieve, and it gives them more time and leads to less wasted time during this process.
Due to the lack of electrical components in our system, we don't have any repair or maintenance costs to really worry about. So that led to our total cumulative cost to be around $26K. which is relatively low, especially when you take into account that the average cost per square foot of a hot cell is usually $20,000 per square foot. That number comes from a nuclear company called LANL. And if you look at this from like a $1 billion lab's perspective, this number 26,000 is actually fairly economical.
For the market, we have the total addressable market, the serviceable available market, and the serviceable obtainable market. For our total addressable market, we're looking at the entire nuclear industry, which is valued at around $2.1 billion. This is all accessible to us, and for the serviceable available market, that is the hot cell equipment. We're using this as a hot cell equipment, and that market is addressed at $150 million. Now, I use an ML modeling machine to see the serviceable obtainable market. For our specific product arcs, in a 5-year period of time, we're looking at $25 to $45 million in these specific markets.
Our financially efficient design allows us to have more effective safety and long-term impacts. As for the safety impact, we're able to minimize the amount of movement and transfers that are needed, as well as reducing the amount of time that humans are interacting with radioactive material. And we are also reducing the amount of waste that we're using by reducing the amount of material needed to move the Americium, as well as reducing the amount of contaminants that the materials are interacting with. We're also having a long-term impact by the scalability and modular design of our project, as we're able to size up the table or add multiple furnaces for future uses if you wanted to create more and with further production, all at a lower risk.
Thank you so much for listening to our presentation. I'd like to thank the Los Alamos Laboratory and the Meloy program for allowing us to gain an understanding of how Americium works and being able to present our project. Our design is very implementable in the current industry, as well as the labs, because we're using parts that are already there. So thank you so much for listening to our presentation.
Questions for Team Art? Can you come to the prototype table and just point to the elements that are part of what you're going to be implementing?
Yeah, we'll go through the process. So this is the valve, the butterfly valve that we were talking about. This would open pneumatically through this pneumatic actuator, or pneumatic actuator. It would open, and then it would go onto the.
So in this case, this is the model of the crucible, and the resin actually falls into the crucible. The linear slides are able to move it. The current dimensions are what we have right now. However, it can be scaled to any dimension, any size, and then the operator is able to push it back and forth with this handle. These handles were specifically designed so the pincher can attach to it and move it back and forth. And then we also have a 4-bar linkage mechanism to raise the axis height. This was done as we wanted to ensure there's no intricate locking mechanisms at the actual heat source in the furnace, and we have the axis change so that we can have a lip on the crucible that we can actually pick it up and lower it down without touching any other components.
Yeah. So the linear slide is going to go on the carousel itself. So it goes onto the to the linear rails in the crucible, and then it changes angular, and then it goes to the crucible, which would say be right here, and it slides out through the mechanism of the manipulators, and then we can put it in the furnace.
And the reason why we use the circular table is so that we can have multiple furnaces and multiple columns. So this increases efficiency quite a lot.
It is the furnace part of your design?
No, we just go from the path from this to the furnace.
But we did have a mechanism where we could just use 1 degree of freedom, which would just be longitudinally with the manipulator just like on that racket and pinion. So it just opens automatically.
Got it. Thank you.
Yeah.
the product from the furnace back?
Yeah, so once the Americium oxide has been created in the furnace, we're then able to have the operator move the slides in and and then we can actually have the crucible stripping mechanism right next to the table. So it acts like an assembly line where we can have multiple processes in the same location, which greatly speeds up the efficiency of our process.
Anything else, judges? Okay, thanks, team. All right, team. Is it Van Lama? Okay, come on. Good job. So just get settled in. Okay, team, whenever you're ready.
Howdy, I'm Mariah.
I'm Ashwin. I'm Nathan. Aditya. I'm Aditya.
Valentina. And we are Venema.
Deep within the world of nuclear science, there is a material of incredible promise. Americium, a power source for medicine, a guardian for industry, a resource too valuable to let go to waste. But to harness this power, we must enter the most dangerous place on Earth, the hot cell. Here, a furnace purifies the material, a process of intense heat and pressure, where the line between control and catastrophe is razor thin. And when that line is crossed, containment is just a word. The fire escapes. An invisible poison fills the air. A silent killer, unleashed. This is a disaster you can't see, and you can't outrun.
It's burning my
But what if all of this could have been prevented? What if the disaster was already over before it ever began? That question led to the creation of Vanema, a ventilation and aerosol neutralization for Americium manufacturing. It is more than a vent. It is a sentinel, an automated guardian that anticipates the chaos. It contains the fury of the reaction. It controls the unstoppable force. It protects the world outside from the danger within. Vanema. Contain. Control. Protect.
Now, while the chances of a widespread nuclear explosion are very slim with this, the threat of having improper ventilation is humongous. First off, you could have toxic fumes that are released into the environment, which goes against EPA regulations if you have a system that is improperly fit to filter out the toxins. Next, the combustion that could occur if it is not properly able to cool down the fumes that are released before it goes through the filtering process, which overall can increase the health risk, because if you also have a mechanism that is not, if you also have a ventilation system that requires high maintenance, then you have to have people go into the hot cell frequently, which increases the radiation exposure and the health risk involved.
We focus on 6 design constraints. First, the hot cell. You have the furnace inside the hot cell. We burn the resin in the hot cell at a temperature of 800 degrees Celsius with a 1 liter capacity. The fumes from this burning are vented out by the vent pipe. Using these 6 constraints, we created 5 design requirements. The first and foremost is combustion control. We don't want a large fire to break out. 2, particle capture. We don't want radioactive dust to escape. 3, safety. We want the workers and the nearby residents to be safe. For efficiency, we want the process to be efficient as possible. By longevity, we want our solution to last as long as possible.
Now, before we actually move into the design, I would like to walk you through some of the key considerations that we evaluated, but eventually decided against it. First, let me talk about the concept of heated highways. In this idea, we will have heated elements placed inside the pipe internally. And the reason we do that is because the outputs from burning the resin include tar, soot, and slag. These kind of materials, they love cool surfaces. So if the pipes internally are cool, they like settling down and accumulate and clog the pipe. So for this, we have a heated highway. This idea sounds good on paper, but to implement this is quite complex, and the operation requires having sensors that monitor the heat. Next, we also evaluated the existing architecture and infrastructure for the furnaces and the vent stacks. And the issue here is that they are not designed for specifically Americium's processing. They, although are good with whatever they are doing, the outputs from Americium processing cannot be used with these existing vent stacks. That is where we have designed Banama.
So we have distributed the design in two phases. The first design controls the combustion, and in controlling the combustion, the first step which we have included is the flame arrestor. So what a flame arrestor does is whenever there's a flame or any a spark coming up from the furnace, the flame arrestor is able to control the spark and does not let it go forward upward into the filter. Then we have a controlled agglomeration process. So what it basically does is introduces an inert gas which allows the heavy Americium particles to collect and basically gather and store down. So it's we are able to remove it easily. Then we have the coolant system, which is wrapped all around the vent stack, which is able to cool the whole system. So in order to decrease the temperature of the flame from 800 degrees Celsius to the operating temperature of the filter. Then we have the phase 2.
So here is the phase 2 design, which is of the final foundation. So here we have a cyclone filter. In the cyclone filter, we'll be having the aerosol particles along with the normal gases. Now, using this cyclone filter, what are the aerosol particles are there? Those will be settled down using the centrifugal force. And what are the remaining gases will be pumped out. Now these gases will be sent to the filtration process. In this filtration process, we have a pressure sensor before and after the filtration process. These sensors will make sure that the filters are working fine. And in the filtration process, it's like a two-stage. The first one is the HEPA filter, which removes all the radioactive dust particles. And then we have the catalyst to remove the other harmful gases. And then that is connected to the duct. It goes to the final exhaust pipe. And even though we have a final working prototype, so we thought, why can't we add some of the safety features here? What if we observe some kind of a fumes in the EP system? That's where we introduce the redundant path to avoid the existing pipeline to make it damaged, so that the existing pipeline will be the intact one and which will be the long lasting.
Our design is focused on safety. So we want to prioritize the protection of all the members that are working in the manufacturing of Americium. Through the different features of Banama's vent stack, we guarantee that. We prevent combustion, which reduces the possibility of the hot cell window to explode.
which also reduces the possible exposure of the workers to radioactive material. Our design also lowers the human maintenance, which leads us to the next point, which is increased efficiency. So with less human intervention, we have a faster process and faster timelines when talking about processing Americium. We also have mechanisms in place, as explained before, to keep the operations going, even if the filters get flooded, and even if the filters get flooded, and it is designed to filter out all the harmful chemicals in one cycle, which leads us to the final point, which is it significantly minimizes the environmental contamination, which not only helps the animals but the entire world. Thank you.
Questions for team? Come on.
Can you describe the prototype?
So here's the main chimney, and beneath it would be the furnace. So basically, the curved structure of the chimney, as you can see over here, would able to facilitate the flow easily into the vent stack. And this is the separation between the hot cell, like below is the hot cell, and here is a completely different area. So and above the chimney is the flame arrestor, which I discussed. So the flame arrestor does not allow any of the flames which have by any kind of abnormality may go to the filter. So the flame arrestor stops the flames from going up ahead. The blue threads that you are seeing here are the cooling system pipelines, which would regularly flow refrigerant throughout a system, which would allow the cooling of the hot gases from 800 degrees Celsius to 240 degrees Celsius, which is the working condition for the HEPA filters. Right here, you see is the EP system, which is the emergency protection system. What basically it does that even though we have the flame arrestor, there are chances that due to high temperatures over here, there might be chances of sparks. So what the EP sensor does, it basically detects it and closes the valves on both the sides of the heat stack, preventing the flame front or the pressure wave to go into the filter or either into the furnace. And it will release an argon gas, which would put out the flame. Up ahead, we have the cyclone filter. So the cyclone filter basically forces the gases to go in a centrifugal motion in order to allow the heavier particles to stick down and allows the gases to go up. Above that, we have the HEPA filter. So the HEPA filter basically eliminates 99.97% of the harmful emissions which come from the gases at a scale of 0.3 micrometers. And after the HEPA filter, we have a catalyst which would be able to remove other harmful gases like NOx, SOx, carbon monoxide, and water vapor. And above, we have a dry screw vacuum pump, which is able to handle a huge amount, which is able to create a huge amount of vacuum even at high loads.
The second handle you see, or tunnel that was added as we kept increasing, how can we ensure safety? We say that we want to maintain safety, but how can we do that? Since the main purpose of this was to prevent the worst case scenario, combustion, fire, all of that. So while these systems, the fire arrestor handles, the flames, and all of that, you don't want to just close off the system entirely. Because that means that the toxic fumes that are coming from here would then be released into the hot cell, possibly causing an even bigger catastrophe. So these valves here would automatically close with the sensor. They come over here, and then there are valves here that would open up, which allow the emissions from here to also come through this secondary filtration system, bypassing the main component of filtration and then being released into the facility's air system.
Is this entirely passive, or is there anything that the operator has to view the system?
Basically, like the building's ventilation system, it's always operating the same way this is going to be operating the whole time.
Additionally, another way that we ensure that there is reduced maintenance is that this is an automated system that can clean itself through the use of sodium hydroxide. It can clean off our main issue of residue being stuck against the walls. So the times that the furnace will be non-operational, because by our research and talking to the mentors here, they said as of now, it runs once a day for 5 to 6 hours, 3 to 4 times a week. That means in the downtime when the furnace is not running, this system will employ the wet caustic solution that will clean the walls, reducing the chances of it being backed up, with the coating also along inside the pipes of a polymer, which allows for the steel that this is made out of to last longer and prevent corrosion.
Maybe one more.
Caustic solution get discharged into the waste stream.
So there will be throughout the system at multiple stages, and there are multiple stages. Like this is a demonstration purposes, but between each section there will be flanges where all the systems will be connected, and at all levels, sodium hydroxide solution will be released at the surfaces of the pipes. What sodium hydroxide solution does is it basically wipes off the remnants of the aerosol particles which get stuck up on the walls. So it cleans the pipes.
Okay, thank you, team. That's it. Burn off my quick. All right, well, you made it. Woo! Good job. Great job. A little more detail about what's happening now. Judge is going to finish scoring. Judges and I are going to go next door. You're going to have a QR code. Oh, I know a guy. Here it is. You are going to jump on that. You're going to take care of all that voting and survey respondings. We are then if you need to take a break of the rest of the to do that, but do it all quickly because we want to gather back here as quickly as possible. We are going to, before we do the award ceremony, we're actually going to go to the learning stairs, take photos, and then we'll come back in here, do the final award ceremony, and then we're going to clean up. And I'm just going ahead and tell you right now, this is the sloppiest group we've ever had. We got stuff spread all over Hell's Half Acre, so you got a lot of cleanup to do. I don't want your computer and your iPad and your, earbuds or whatever. So I want to keep all your stuff. Okay. All right. You guys fill that stuff out. Judges, let's go next door.
So that's a
So get in and around this night. Nobody's ready. Oh yeah, but now we're going. I didn't check any bags. But it's used to
Yeah, I don't have any, but it's like to me it's on top of my planet. You're better put the tags to the ducks. There may be reproductive situations. You're not one of them. Online, how college is like a some of the big
Yeah, I mean, presenting can be stressful.
Speak on.
I like the idea of we had like more
Army stairs. Army stairs. Let's go.
believe you're that might be that's a good idea. Thank you so much.
Interesting. Let's go. Got this. They're already smiling. Hurry.
Hey, the photographer's not down.
Why am I not surprised that Scott is the biggest problem back here? Yes. Yes, I am. Okay. I'd like students. I'd like for us to say thank you to a couple groups. First, let's say thank you to the judges for being here. There's at least a chance they had something better to do on Sunday afternoon than hang out with us, so it's really kind of them to do that. And then I'd like to specifically acknowledge the 4 mentors who spent all weekend with you. How about that? And how about the Meloy team that has fed us, take care of us, they got us out. So what I'd first like to do before we start into the awards, like the 16th thing that I've injected before the awards. I'm just trying to build suspense. I'd like for you to hear back from the judges, not team by team, because you don't get to see what I get to see. You don't get to be part of the deliberations that I get to be. But they've got some thoughts on what they saw, the good, the bad, the ugly. I have asked them to be pretty open and honest with you. This is, because they're not going to call you out by names. So maybe we could start with Evelyn is on this. Stand up and tell them the story.
That wasn't very fair.
Yeah.
I thought you were going to go left. First off, I think I can really say we all could tell how hard the teams worked over the last couple of days. And the importance of the mentors being here and connecting with you as well. So great job, everybody. The one thing I guess I would say in thinking about like glove box operations in a nuclear facility operating environment is materials compatibility and waste streams are also important to think about. So when you're introducing liquids or solutions into a process, think about how you're managing that and how the different materials might react or interact. So.
Okay, good. Thank you very much. Don?
First of all, for those of you who are doing an event like this for the first time and you're really surprised by how chaotic it is and then all comes together at the last minute, that's always the case. And I'm sure for those of you who are in capstone or going to be doing capstone, you'll go through the same process. So it's all natural. The one comment I wanted to make is all of you had, probably because you were prompted to do so, you had to do a design trade-off where you had to show, here are the concepts we brainstormed, and concept 1 sucks for these reasons, and 2 sucks for these reasons, and 3, which is the one we're going to describe, is absolutely perfect. Love it. But in reality, after you've done the down select, it's actually good to turn the tables and say, what's the problem with my concept? Right? So don't fall in love with it so much that it comes across as perfect, because no design concept addresses everything. And the more you dig, the more you'll realize that by identifying the weak links in your concept, you can actually make it stronger. You can go back and reinforce it. But I thought you guys were outstanding. Thank you.
So they touched on some technical things. So I'm actually going to touch on some of the presentation style things. And one thing that I liked when I probed was you actually had answers most of the time. There were defensible things that you had thought about, which that's great. Like some of those things I would thought, no, there's no way that 10 times, that's just a number, right? But to be able to actually say, well, this is why, that's really great. It shows that you understood, where these things were coming from, what was important. What I also noticed was sometimes it seemed like you didn't understand the question, so you'd answer something else. And so a strategy, if you think maybe you're not quite there, you can repeat the question to people. You can say, let me make sure I understand what your question is, right? So that you can not waste time just going through a bunch of things that we didn't actually ask about, and then miss the point.
Great, teacher. So for our 4 mentors that have been here all weekend, David, Jack, Scott, Eric, could you guys come up here for just a minute? Crates of rotten tomatoes. Now's your chance to get back at them. I'm just kidding. I'd like to give you gold medals. You are so welcome. You guys have been great. All right. Now to our People's Choice Awards. For the People's Choice, these guys have lots of gold trophies, I'm sure. For the People's Choice Award, each student will get a $25 deposit in your student account. If you don't know this already, the only mechanism we have to pay you anything is through your student accounts. So you'll get a $25 per student deposited in your account. So just for these awards, let's just stand up right where you are as a team. Let us congratulate you. The first award for the most feasible solution goes to Team Project Illumina. Thank you very much. Okay, our next award goes for the best prototype. And oh, by the way, you guys kind of leaned into that prototyping stuff. Good job. I mean, 3D printing is kind of stuff. Is Mr. Fab Lab even here? There he is, Mr. Fab Lab. We give you a trophy, but we have to ask you to print it out. So, all right, the best prototype goes to Team Arcus. Next award is for the best video. Again, we've been doing this long enough where we used to have to help students with videos. And that's a bad day at the office when we're trying to help you with the videos. Yeah, that's not the case anymore. You guys you're the stuff. Best video goes to Team Arcus. Congratulations again. Let's see, 25 and not carry that. You're at the $50. Best presentation. So the best overall presentation voted on by your peers. It's a pretty significant deal to win award from your peers. Goes to Team Arcus. You didn't like submit like 6 votes like people in Louisiana, nothing like that. The last award before we get into the cash prizes is one that actually is from the mentors, and it's for the team that had the most teamwork. Regardless of how you place, regardless of how you do, learning to work in teams, I think you would hear it from every mentor. I think you'd hear it from every judge. It's the stuff. It's what life is all about, whether you like it or not. And this is exactly the way it works in teams. You don't get in corporate America to go to your boss and say, I'd like to have, I don't want that. This is what teamwork looks like. Okay? A bunch of people you don't know might have different goals and objectives. You got to figure out some way to kind of coalesce, come together. You win or lose together. Best teamwork goes to Team Arcus. Now to the cash prizes. The cash prizes will be the amount divided by however many people on your team, also going into your accounts. After you receive your award, stand here for a minute. Mr. Cook's going to want to get your photo. Third place, prize of $1,500 goes to Team Actonite Solutions. Kind of stand here in an arc like you did when you were doing. Gonna hold up this check. You cannot have the check. We have to keep this. It's cost us a fortune. In fact, we're going to deduct it for out of your prize wins. Congratulations. Good job. All right, so you guys gather all around here.
Let's fit in front of the banner.
In front of this banner?
Yes.
Okay, so rotate. There you go.
There we go.
Here, my fall guy. All right, make sure the check is nice and parallel to the ground.
All right. 3, 2, 1.
Perfect. All right. Second place. Cash prize of $2,500 goes to Team Revolver. Crowd's favorite. You guys hold this up?
Don't want to scare
Yeah, no, that was so cool.
Yeah, a little more.
It was so seamless.
This is the game. Don't worry about the problem. Perfect. Thank you very much. Congratulations. First place for the $5,000 award for the 2026 Los Alamos National Lab Aggies Invent goes to Team Marcus.
Yeah, man. Good for them. David in the middle too.
You want crazy. So much in the middle. Everybody we had space in here.
All right. Smile. Oh, there we go. Done. All right.
That's it. Public service announcement from your parents. Go home, do your homework. Okay, thank you very much for being here. Stop by and say thank you again to the judges. Say thank you to the mentors. Clean up your stuff in every room. Leave nothing. Thank you. Have a great weekend.
And they're not in the right, like, they have to read the sandwich because it's.
Thank you so much.
You don't need it, I think she wants to interview. Yeah, you already got it. Did you tell